Alright, so I thought I was almost done with this series. I only had 4 more shaders to cover. But then I started experimenting more with these shader tricks, the fake lighting and using different procedural effects that I hadn't really used before in 2D shaders. And yeah, this video kind of exploded with new stuff I just had to share. If you've followed along in our first 3 videos, you already know the basics of scaling UVs, working with fragment colors, moving corners and vertex functions, and even adding procedural noise and time-based animations. But today we're going to stack all the stuff we've learned in the series, plus learn a few new techniques like Swizzling, Mipmaps, and fake lighting, and even drawing effects outside of a sprite's original bounds. We're going to see a bunch of vector math in this code, but we won't focus on it too much, and instead I'll try to do my best to help you visualize how the working parts come together to create the final effects. These aren't just little shader snippets, they're full-on mini effects that you can drop in and customize for your own projects. Ghosts, blobs, portals, and waves. Let's get to it. Alright, first up is the GhostEffect shader, and this time we're adding some custom enhancements to the original shader found on GodotShaders.com. The goal here is to make a sprite drift up to the sky and fade out like a ghost, but with an extra twist. We want the effect to render outside of the original rectangle bounds of the sprite. By default, fragment shaders only render within a sprite's mesh rectangle. That means shader effects can't extend beyond the sprite's borders. Common workarounds involve layering a second sprite, or even using particle shaders for more control. But this shader uses a more direct method, modifying the mesh in the vertex function. The mesh's corners are pushed outward by scaling the vertex positions, doubling them in this case. This expands the rectangle from a 0 to 1 range to a 0 to 2 range, giving the fragment shader more visual space to work with. However, scaling the mesh creates a new problem, UV distortion. The UV coordinates remain tied to the original 0 to 1 range, so the texture appears stretched out across the larger mesh. To correct this, the shader rescales the UVs in the fragment function. It recenters them by subtracting 0.5, scaling the results by 2, and then adding 0.5 back. This remaps the texture to fit cleanly and centered within the expanded space, preserving the original image while still allowing extra space around it for effects. Next, color swizzling is used to shift and remap colors and vector channels. Swizzling is a common technique, and we've already used it in previous shaders, we just didn't have a name for it. In this shader, the RGB components of the main texture are swizzled. Green becomes red, blue becomes green, and red becomes blue. This alters the sprite's tint, giving it a ghostly hue. Swizzling can be done with any combination of vector components, so if we wanted to, we could do something like take one of the original channels, like red, and put that single value into each of the R, G, and B channels, giving us a grayscale effect. Or we could put the alpha channel value into each of the channels, giving us an alpha mask effect. The components can be used to store other data as well, not just color components, but we won't do that for today. Anyway, the goal of this swizzle is to make the original sprite change tint, but we could easily remove or change this swizzle if we wanted to. Okay, here the ghost's vertical position is controlled by an input setting, the ghost progress uniform. At 0 progress, the ghost overlaps the original sprite. As the progress value increases, the ghost floats upward, moving halfway up the expanded mesh. This simple vertical drift is a key part of the ghost effect, and the progress input setting is how Godot will animate the effect. To add a blur or pixelated look to the ghost, the shader uses Mipmaps. Mipmaps are pre-computed, lower resolution versions of a texture that help make things look better when images are zoomed out or if they're far away from the camera. But we can also use them to create blocky, pixelated, or blurring effects, which is what this shader is doing here. For 2D textures, Mipmaps are not automatically turned on, so you need to tell Godot that it should pre-generate the low-res versions. If you're looking at the texture in the inspector, it'll show you how many Mipmap versions it has. If it says no Mipmaps, you'll need to re-import the texture. To re-import, first open the texture in the File Explorer, then click the Import tab near the scene tree. Then, in the import settings, make sure the Generate Mipmaps option is checked. Finally, click the Re-import button. Once generated, Godot will list how many Mipmaps are available. This example uses 6. Next, the sprite's texture filter should be updated to a mode that supports Mipmaps, like Nearest Mipmap or Linear Mipmap. Nearest Mipmap gives a more blocky, pixelated look. Linear Mipmap results in a more smooth, blurry appearance. We could spend an entire video talking about Mipmaps and texture filters. But for now, remember that using the nearest filter will give you a more pixelated granular image. And using linear filtering will do some magic to create new pixel shades that did not originally exist in the original image, giving you a much smoother blurring effect. I'm showing both examples here just to give you a feeling for how they look different while the images are scaled. Now, with Mipmaps available, the shader uses the built-in texture load function to sample the texture at a specific Mipmap level. This function works like the texture function, but allows manual control over the blurriness or sharpness of the image. The Mipmap level is calculated from the ghost progress value, starting at Mipmap level 0 and increasing up to Mipmap level 4.5 as the ghost rises. This makes the ghost appear more blurred or pixelated the higher up it floats. For color, the ghost texture is then swizzled, this time using the red channel to create a grayscale version of the original sprite. The brightness is also increased slightly to enhance visibility. The transparency of the ghost is also controlled using the ghost progress uniform. At 0, the ghost is fully opaque, and as the progress reaches up to 1, the ghost becomes more transparent. This gives the effect of a natural fade-out as it rises. This next section fixes an issue I encountered with some textures. It's not always needed, but it's useful to know about if you run into it. Because the mesh was expanded, there's a chance that pixels outside the original texture bounds could be sampled incorrectly. If the original image had edge pixels right up against the border, they can sometimes smear or stretch out visually. To avoid this, these bounds checks verify the UVs. Once UV coordinates fall outside the 0 to 1 range, sampling stops. This prevents the visual artifacts and keeps the ghost effect clean. In the final part of the code, the shader mixes these two layers, the original sprite with its tint adjusted via swizzling, and the grayscale ghost image, fading out and drifting upward, depending on how high the ghost progress is. The result is a cohesive ghost trail that lifts off the sprite and vanishes up into the sky. The ghost progress uniform can be animated using Godot tools like tweens, animation players, or scripted logic. The effect scales naturally over time and can be adapted to different speeds or trigger conditions. It also pairs well with other effects, such as a spooky wobble or the teleport shader shown later in this video. It's a great example of combining vertex manipulation, UV scaling math, and Mipmaps to break outside of the limits of a single sprite, while also getting cool blur and fade effects. Okay, let's move on to the next shader. Next up, the TeleportDissolve effect shader. This shader pulls together several concepts we've covered earlier in the series, like noise, UV scaling, and step functions. But this time we're using them to create procedural dissolve effects, perfect for making a character zap out of existence or appear out of thin air. Like the last shader, this one lets you control the progress of the effect using a uniform variable that goes from 0 to 1. Here's how it works. The shader begins by generating a 2D noise pattern. This is a simple value noise function, like we saw in the last video, built from dot products and smooth interpolation. It creates a mostly randomized texture across the surface. While basic, this procedural noise serves as a foundation for the dissolve effect. If we wanted more unique noise to get different dissolve effects, we could consider adding a customizable noise as a texture later on. Here, the noise is then multiplied by the y coordinate. This scales the noise vertically, causing it to grow stronger toward the top of the sprite. The result is a directional gradient, where the teleportation begins at the top and travels downward through the object. Then comes the key parts that drive the dissolve behavior, two step functions. The first step compares the noise value at each pixel to the teleportation progress uniform. Pixels where the noise exceeds the current progress are fully removed, simulating the part of the sprite that's already teleported away. The second step creates a narrow band just along the edge of the noise. This produces a beam of color that marks the active teleportation front, adding some visual flair and a sense of motion. That beam can be customized. Here it's multiplied by a color uniform. So whether it's magenta for magic, cyan for sci-fi, or any other aesthetic, the glow can be adjusted to match the game's tone. Finally, the texture's alpha is gradually faded behind the teleportation front. This gives it a soft, smooth appearance, blending the sprite into the background without harsh edges. By adjusting the progress over time, Godot can animate the whole thing using animation players or tweens, or by just driving it with the shader parameters in the inspector if you want something self-contained. You could even combine this teleport shader with the ghost effect from earlier, making a ghost trail linger for a second after a teleport. Or you could even reverse this teleport progress to simulate the sprite teleporting into your world, instead of dissolving out. Small effects, but really versatile, and they look great. I hope you have fun with that one. Okay, next we're jumping even further into procedural territory. Let's make LavaBlobs. This shader uses random numbers, distance threshold calculations, and soft gradients to simulate floating blobs inside of a lava lamp. Here's how the pieces come together. The shader begins by creating the background. This will represent the clear liquid in the lamp. Instead of a flat color, it uses a horizontal gradient across the x-axis. A mix function blends two color uniforms together, based on the UV's distance from the center. This creates the appearance of depth behind the blobs. The background's transparency is then adjusted using a separate background alpha uniform. Then we have the option to turn off the blobs completely. If we do turn them off, the resulting image will still have the customized background color, but no further logic is performed. If the blobs are enabled, then the code continues to create and manage those blobs using several helper functions. A procedural randomness function is defined so the shader can produce consistent but random values. It hashes a 2D vector using a combination of dot, sign, and fract function calls. The result is a pseudo-random value between 0 and 1, based on the x and y coordinates that we send to it. The random seed uniform is also used in the generator, to ensure that each instance of the shader produces different results, while still remaining consistent internally. This random function is used for the positioning, the speed, and the size of individual blobs later on. Next, an oscillate function will control the vertical movement of the blobs. It returns a sine wave, mapped between 0 and 1, taking time, speed, and a random phase offset as input. It also is given an upper and lower limit to control how far the blobs will move. This gives each blob independent vertical motion, rising and falling continuously, like bubbles in a lava lamp. Now for the main blob creation logic. The shader declares a constant size array to store the blob data. For each of the 6 blobs, the shader assigns 3 values into a vec3. The horizontal position, randomized per blob, the vertical position, animated and randomized using the oscillation and random functions, and the radius or influence factor of the blob, which is also randomized. These values are stored in the vec3 array called blob centers. The shader calculates them in a loop, allowing multiple independent moving blobs to be managed at the same time. Now that we have the blob centers, the shader needs to merge the blobs together to get the distinct lava lamp effect. For each pixel, the shader computes a cumulative influence from all blobs. This is done by measuring the distance between the pixel's UV and each blob center. Each blob's influence is based on its radius, divided by that distance, ensuring a stronger effect closer to the center. In the loop, all blob influences are summed together for the pixel. The result is a smooth distance field, where the influence fades naturally as it gets further away from the blobs. The shader gives even more control over the distance calculation by giving you uniforms to control the blob scale in either or both the x and y axis. Next, the shader adds colors for the blobs. The classic look of a lava lamp has brighter blobs at the top and cooler, darker blobs at the bottom. So here the blobs are given a vertical color gradient. Using the current y coordinate, the shader blends between 2 customizable color uniforms, one for the upper blobs and one for the lower blobs. This creates a fluid gradient that changes as the blobs move up and down in the lamp. And finally, once the total influence is calculated, and we have the blob color for the current pixel, the shader checks the influence against a threshold. We can configure this blob threshold uniform to make blobs bigger or smaller. Pixels with influence above the threshold are rendered fully as the blob color. Those below the threshold are blended softly between the background and the blob color using a smooth-stepped powered curve, giving the illusion of spherical depth. The result is an organic fade between the blobs and the background, with soft edges that merge naturally as more blobs get closer to each other. And there we go. Lots of uniform settings you can play with to get some interesting patterns. Some of these don't even look like lava lamps and are pretty unique. And finally, our last practice shader. It's a good one, the WaterWaves shader. This effect layers multiple procedural wave functions, calculates a height map, approximates surface normals, and even does some simple lighting tricks using vector math, all inside of a 2D fragment shader. Don't let the code fool you though, there's only a few important components that bring this shader to life, and I'll try to keep it easy on the math. Before we get too far into the shader, first let's look at these define statements. In shaders, define is a preprocessor tool that lets you create shortcuts before the code is compiled. It's useful for two main reasons, readability and portability. For example, this define replaces all instances of tau with the appropriate value, making the math a little bit easier to read. Similarly, this define here allows the shader to use shader toy and other shader language variable names, making it easier to reuse the code across platforms. In many ways, define is similar to using a constant. Both let you assign a value once and reuse it. But define doesn't have a type, and it's handled as a text replacement during compilation. This makes it lightweight, though less strict than type constant values. Defines also let us tweak coarse settings in one place, like defining the number of waves here. Handy if you want to adjust how many layers of wave motion are combined, without digging through the entire shader. Think of them like global settings or shortcuts that can simplify both coding and experimentation. Okay, let's look at the code in more detail. Each wave in the shader is driven by procedural math, specifically trig operations that act like animated sine waves. But instead of a single ripple, the shader blends many waves together. It uses a concept called superposition, where multiple waveforms of different scales and angles are stacked together. Each wave has its own frequency, amplitude, direction, and phase offset. This randomness comes from the golden ratio-based angle, phi, ensuring that waves don't line up in repetitive or symmetric patterns. The result is an intricate interference pattern, ripples of different speeds and sizes interacting over time, giving the appearance of overlapping waves in a pond. The height function accumulates all of these waves into a single floating point value for each pixel, creating a dynamic, time-evolving height map. Think of it like drawing the elevation on a flat surface with using nothing but math. Now that the shader has a height map, the next step is to approximate the surface normals. A surface normal is the direction immediately facing outward from a flat plane. But since this is a 2D shader, it doesn't really have a surface mesh to sample from. It only has our height map. So it uses a technique called finite difference approximation for the current pixel. Imagine comparing the pixel to a point slightly to the right and measuring how much the height changes, and do the same for each of the directions. Those height differences give us a slope of each pixel in x and y. These tiny gradients are treated like a pair of tilted lines, and by taking their cross product, we can reconstruct a 3D normal vector. This gives us something similar to a normal map, except it's calculated entirely from math on the fly, no texture required. It's a powerful trick, dynamic normals from nothing but a height function. So now we know which direction is facing outward for each of these pixels. With the surface normals calculated, lighting becomes possible. The shader uses a directional light vector, like a fake sun above the water, and compares it to the surface normals using a dot product. Dot products are common math tricks useful in shaders, and especially for lighting. They tell us how aligned two vectors are. So when the surface normal points directly at the light source, the result will be bright, while the more it faces away from the light, the darker it becomes. This gives the water a soft dynamic shading as ripples roll across the surface. But there's more. The shader also uses a cross product when building the normal itself. This adds depth by factoring in the perpendicular direction of change, and in one specific condition, when the surface aligns nearly perfectly with the light direction, it creates a sharp specular highlight. This highlight is the bright sparkle or glint you sometimes see on the crest of waves, and enhances the illusion of reflective water. Together, these simple vector math tricks give the appearance of foam, depth, and shine. After the lighting and geometry are figured out, the final pixel color is constructed by blending several components together: the sky, the water, the foam, and the specular values. There's the base texture, the original water image or color tint. On top of that, it blends in a subtle sky tint based on the surface angle, helping simulate light coming from above. If the water is nearly flat and facing up, it appears more reflective and sky-colored. It also adds the highlights for foam, and the sun glints using specular color. These bright spots help sell the wave motion glinting in the sunlight. And finally, the entire output is faded out using a customizable alpha value. This transparency tweak can be used to layer the water over a background, or tune the effect's intensity. Because the whole pipeline is modular, we can tweak the base texture and the lighting colors, or even remove the texture entirely, making this a flexible template for anything from magical fog to sci-fi energy shields. You can easily rework this for lava flows, swampy lowlands, or other fun patterns with a little color tweaking and texture tweaking. And that's a wrap on this shader mini-series. Back in part 1, we started with simple UV scaling, animations and color space tricks, and here we ended with Mipmap-enabled textures, lighting-aware effects, and procedurally distorted features, all in 2D, all in Godot. If you followed along, huge congrats! You now have a toolkit of shader techniques to mix, match, and layer your own visual effects together. And honestly, I'm still learning too. Every time I pick apart one of these shaders, I discover something new. If you make something cool with these techniques, please share it in the comments or tag me online, or even post it on GodotShaders.com for others to enjoy. I'd love to see it. Until next time, keep experimenting, keep breaking stuff, and never stop learning. Thank you for watching the Pathfinder's Codex.